Hello, Garrett. I'm Doug. It's very hard to communicate technical ideas, so my thought was to walk through your paper, An Exceptionally Simple Theory of Everything, because that would provide us a common ground for communication. But let me start by giving you a mini introduction to myself. I'm a skeptic. I like to bash ideas and see them break. But I am also a fringe physicist, meaning I have no degree in math or physics, and yet I'm trying to make a contribution to the field. The odds of succeeding are not good, and I have to live with this internal conflict. Most fringe physicists are simply old men with bad math. Now, in my defense, I do have degrees in biology and chemical engineering from MIT and a master's in software engineering from Brandeis. While I was working as a biologist, I was able to take graduate level classes in physics at Harvard, MIT, and BU. Boston is a great city to take classes in. And part-time, I have been doing research for more than a decade. And my focus happens to be on quaternions. In fact, I even own quaternions.com. Now, the goal of this exchange is to see if we can establish a working relationship. My email box is always open. I really like Skype because I think chatting is just much more efficient than almost anything else. So let's look at the paper. And what I like is we get into issues straight off the bat. Sentence number 2 says, but which math? Well, your answer is that we should use group theory, and in particular E8. Now you might guess, oh, he's just going to say quaternions. But my answer is more subtle than that. Or more subtle is actually more fun. And that is, I'm thinking about 4-dimensional tensors that have inverses so that one can do group theory. You argue that the math should be beautiful. But then that opens up the question, what is beauty? Here's my definition. Beauty is complexity with purpose that leads to simplicity. Here is a clay sculpture I did a number of years ago. It's called Beth because, well, that's her name. And when I was doing this, I noticed that the skin was moving over her ribs, because of course that's the way breathing works. Now I completely missed that in this clay representation. See, human beings are amazingly complicated, and yet their purpose is life. And that leads to the simplicity that I tried to capture with this clay sculpture. Sorry, but there are going to be no more images of naked women throughout this discussion of mathematical physics. But I had to put that in there to try and, bump up the number of people who would watch this thing. So, returning to the paper, is it beautiful? Well, by this definition, E8 is complex. It's got 248 real dimensions. If you write out all the polynomials for it, it's 60 gigs. Now the purpose is to unify the 4 known forces of nature, and that leads to its simplicity, which is one principal bundle connection and its curvature. So this paper is beautiful by the definition provided here. Now, whether it's right or not, that's a different issue. You then start to address the 2 big pillars in modern physics. That would be the standard model and general relativity. Now, I'm going to add a key qualifier to one of your sentences in here. Any attempt to describe nature at the foundational level must reproduce these successful theories' experimental predictions. Now, I know you understand this point because you reference experiments just a little while later. And yet, I think you want to leave the standard model and general relativity completely unmodified. I'm actually going to try and compress them both at the same time. You provide a warning. The further we drift from these experimentally verified foundations, the less likely our mathematics is to correspond to reality. Now, I take that as a polite dig for people who work on strings. Now, I'm a fringe skeptic, and here's my view. If the units are wrong, the proposal is wrong. The majority of work in fringe physics can be dismissed on units alone. Work on strings has a spacetime that has 11-dimensional meters. If compactification is accepted, that we can somehow go from 11D meters to 4D meters, then any change in units becomes acceptable. So you could just say, well, this particular measure was caught between the bulk and the brain, and so it's okay. I don't accept that. I don't want to lose my best bat to beat up fringe physicists. Logic is harsh on the fringe, and I'm unwilling to give up this key tool, so the harsh tool must also apply to people who happen to work on strings. The units for space-time in strings is wrong. Therefore, all work on strings in greater than 4 dimensions is also wrong. This is an unpolite message from the skeptical fringe. You offer advice on the way to go. The most sensible course towards unification is to extend them with as little mathematical machinery as possible. I'm going to offer a corollary. No new math means no new physics. Now, there's nothing new with quaternions means that there's no possibility for new physics. I mean, it's kind of, in some ways, the big selling point of work on strings. We're doing all this new math, therefore we must be doing all kinds of new physics. Now, people looking at quaternions will say, they are defined, they are old, so they've got no chance whatsoever to do new physics. Sounds reasonable. But I can provide 4 bits of new quaternion math that I have developed. The first one is a quaternion derivative. The limit definition of a quaternion derivative is broken. You don't know whether you should write the differential on the left or the right, so people talk about left derivatives and right derivatives. Doesn't work. They're unable to show that a function like q squared is analytic in q. It's ridiculous. It's no good, all right? So what I did was I developed a 2-limit definition. Let the problem 3 vector go to 0 first, and then let the scalar go to 0. Then it doesn't matter if the differential is on the right or the left. Effectively, what you have is a directional derivative along the real axis. I think this is the domain of classical physics, ordered in time. Now you can reverse the limits, and then all you can actually know is the norm of the derivative. I believe this is the domain of quantum physics that can be ordered in space and not ordered in time, which is what upsets people when they start thinking about quantum mechanics. So the second development is to come up with a Quaternion representation that commutes. That's really just a reinvention of hypercomplex numbers. Now, I don't actually like the label hypercomplex numbers because there's nothing hyper, there's nothing complex. Now here's the 4x4 real matrix representation of a quaternion that everyone uses out there. And what I do is I remove all those minus signs. And this can actually be inverted so long as there's a divisor in here is not 0. And you say, well, what is that divisor? It turns out to be the product of the 4 eigenvalues of this matrix. So if you exclude the eigenvalues of the matrix representation, then what you end up with is a 4D Jordan division algebra. Now, I needed to invent this actually. It was a requirement for gravity, which is a universal attractive force. And this may actually be an important technical difference between your work and mine. You seem to be using Lie algebra to do the work of gravity, and I think you really need to use a Jordan algebra for that force. My third development was to visualize any quaternion function. Now, I applied this to the symmetries of the 4 known forces. That would be U1 for EM, SU2 for the weak force, electroweak, SU3 for the strong force, diff M for gravity. And I was able to put it all in one image. And if you haven't seen my 9-minute discussion of that, please take the time to do so. But the bigger picture is that you can visualize any space-time function whatsoever. And so the big picture really is that there is always an animation. That's not how it is done today. I think our responsibility in the future will be to always come up with some sort of animation for the math we're working with. You provide some more advice in here. And we should pair and unite existing structures whenever possible. That's a great line. And in fact, I think it's the place where we will connect the best. Because I'm looking at tensors as being 4D with inverses. Because that pairs and unites potentials with groups. So tensors are groups under addition. The inverse of a tensor A is minus A. The identity is 0. We need tensors to be groups under multiplication. And if that's a constraint, then we must constrain tensors to 4 dimensions. Now, all experimental data to date in the fields of gravity, electromagnetism, the weak force, the strong force are 4D. So this constraint is consistent with all of our known data. It does block all work in higher dimensions. Now that will not be popular, but being on the fringe, I don't care about popularity. I don't have to get a grant or anything like that. I actually bet this one guy, Lubos Motel, that in the next, was not really bet, it's a payoff. If any time in the next 10 years, anyone establishes to the general agreement of everyone in physics that we need more than 4 dimensions to describe nature, then I will send him $100 check. I think we're in the year 3 or 4 of that. And I feel pretty safe, actually. So all I want to do is grant tensors an additional property, that it can form a product with another one. That can be done in 4 dimensions. And if you look at the covariant derivative for the standard model, what you see is you see a differential operator, you see a potential, you see a group term, and you see a coupling constant. And I think you can get rid of that group term. The way you do that is for U1, you just take the potential and normalize it to itself. For SU2, you take the exponential of the quaternion minus its conjugate. For electroweak, you combine those two. For SU3, you take one electroweak symmetry, conjugate it, multiply it by another. And for diff M, what you do is you say, oh, that S, that's a unit, okay? Well, as I move around the manifold, what I'm going to say is that one can actually take on, it can change from one place in the manifold to another due to gravity. So the math big picture starts from Newtonian calculus. That's the study of change. Einstein's big development was to make things four-dimensional with space-time. Now, if you do calculus correctly in 4D space-time, then the result is the difference between classical and quantum physics. If you do 4D right with multiplication and inverses, you can make connections directly to group theory and be able to see the symmetries of the four forces of nature. Now, in my limited time as a fringe researcher, I have studied one equation in particular, and that would be the 4D wave equation, where by wave equation I mean one with covariant derivatives, so we can look for how the derivative is constrained in how it changes in the wave equation. And I was able to find a solution that involves a dynamic metric. It's known in the literature as the Rosen Metric. I call it the exponential metric because it's exponentials down the diagonal. And it's manifestly more beautiful than the Schwarzschild metric because exponentials are the calling cards of deep physics insights. And the Schwarzschild is just some kind of brief, truncated series, and nothing more than that. It's not pretty, particularly if you put it in isometric coordinates. If you've ever seen that form, it's very ugly. And you can understand why they always write it in Schwarzschild coordinates, because it makes it as pretty and short as it can. But it's nowhere near as gorgeous as having exponentials down the diagonal. And though exponentials have a physical meaning, I mean, it's basically one, except for a little wobbling that you get because your exponent is non-zero. Now, this metric is actually consistent with every weak field test done to date. It also predicts 0.8 micro arc seconds more bending around the sun than the Schwarzschild metric. It also predicts that gravity waves will not be transverse. That's EM. So both of these tests are not possible today, but they are tests of my proposal, unlike anything done in string or loop quantum gravity. And of course there are all these animations which seem to indicate that new math really is happening here. Your work is beautiful and it's challenging. I understand if you decide to keep working at it, and I certainly respect you for doing that. My favorite line actually was right in the middle of the paper, page 16 here. It says, the weights of these 222 elements corresponding to the quantum numbers of all gravitational and standard model fields exactly matches the 222 roots out of 240 of the largest simple exceptional Lie group E8. You know, this was so dry. And yet, I'm sure you knew where you were when you made those kind of line up. It's pretty miraculous. But it is my responsibility to actually reach out to professionals like yourself. Because only so much can be done part-time by a fringe physicist. So my great four innovations on 4D numbers are actually not that great. In the sense that they already exist for the real numbers and for the complex numbers. There's a robust definition of a derivative for real and complex numbers. They commute. There's ways to visualize them, and there's all kinds of different connections to group theory using real and complex numbers. And I'm just trying to take those 4 properties that we already have for those division algebras and make sure they're there for when we decide we got to work in 4D, in Einstein's 4D space-time world. So the take-home message I want you to take home is that if we handle 4 dimensions right for both calculus and group theory, then lots of new physics will be the result. Thank you very much.